51, where 51, what 51 is an exercise in changing the order of integration in a triple integral. Exercise 52 is very similar, and I've assigned it to the tutorial. So let's do 51. It says the figure shows the region of integration for the following triple integral. So you're given the integral. So there are obviously 6 different orders. There's the one given yzx, then there's yxz. There'll be xyz, there'll be xzy, and there'll be zxy and zyx. Okay, there'll be 6 orders altogether. One has been given. The picture is also given. Let me draw it. What do we have there? We have a curve of some kind. That looks like a square. There we have a straight line. Okay, there's z, x, y. All the various important numbers seem to be ones. Okay, let's have a look. What have they given me? I don't know what the integrand is. I don't have to know what the integrand is. They say y is going from 0 to 1 minus x. Okay, so that must mean that this plane over here is the plane y equals 1 minus x. Cool. Z is going from 0 to 1 minus x squared. Okay, cool. So this surface up here must be the surface z equals 1 minus x squared. And x is going from 0 to 1. Okay, there we go. All right, now I need to change the order. So in this one, the way it's been laid out, that sort of parabolic shape on the xz plane was being taken as what I've been choosing to call the base, and y was there for the height. So y went first from 0 to the plane, and then then that expression there just describes this bit. That's region underneath the parabola. Okay, so the easiest thing to do is probably to keep y as the height. And y will still go from 0 to 1 minus x, but let's swap the other, dx, dz. So we'll keep that same parabolic shape, but x will go first. Okay, cool. So if z equals 1 minus x squared, then that means x equals what? X squared is 1 minus z, so x is square root of 1 minus z, plus minus, but the minus would be on this side, and the plus is on that side. So the piece of curve that we are interested in is just the positive square root. So z is going to go from 0 to square root of 1 minus z for values of z that go from 0 to 1. Okay. Now I've got to go for the 3 other orders. I am going to this time consider that triangle on the xy plane to be my so-called base, and I'm going to make z go first. Okay, so let me draw that triangle on the xy plane. It just looks like that. 1, 1, there's y, there's x. That's the line y equals 1 minus x, but similarly it's also the line x equals 1 minus y. Alright, so z is going to go from z equals 0 up to that curvy top. And that curvy top is z equals 1 minus x squared. Okay. And then let's have a look. I'm interested in that triangle now. That's near the bottom of the screen. I'm going to make y go first and then x. So y will go from 0 to 1 minus x for values of x that go from 0 to 1. And it's very easy to flip that round and go dx dy. Okay, that triangle, if x is going first, x goes from 0 to 1 minus y for values of y that go from 0 to 1. You read it off the picture. Here come the hard two. Choosing my yz square as my so-called base. Now you might think, how can that be hard? It's a square. Squares are easy. The square itself is easy, but if I make that square on the YZ plane my so-called base, and my x is my height, and x gets to go first, I've got to say x goes from something to something. Well, x clearly goes from 0, but what does it go to? Does it go to that sort of parabolic sheet, or does it go to the plane? And the answer is, well, it depends. It depends where it's coming from in that YZ square. In fact, let me not write equals here. Let me draw some pictures. I'm going to draw that square on the YZ plane. Here's Y, here's Z, here's the square. Okay? Imagine a point up here. Let me give this board some love. Imagine a point in that square up towards the top left-hand corner somewhere. And then head away from your YZ plane within your three-dimensional shape, which I've scrolled past now. Which bit of your shape do you end up bumping into? If you're up there towards the top left and you head out, what's going to be the furthest extent of x? X is going from 0 to that curvy bit. Yeah, people are doing this with the air with their hands. That curvy surface, what is it, z equals 1 minus x squared, that parabolic sheet. But I hope you can see that if you have a point down here in the bottom right of that square, and you head out, you're actually going to bump into that plane, that y equals 1 minus x. And the dividing line, so basically we need to divide that square into two regions. There's the region that's associated with x going from 0 to the parabolic sheet, and there's the region that's associated with x going from 0 to the plane. And the dividing line, that looks straight, it's not supposed to look straight. Let me try again. That dotted line that I have just drawn there is the YZ projection of the curve of intersection of the plane and the parabolic sheet. See this curve here that I'm now going to do in red? That curve there, that's its projection. It's YZ projection. And that curve is very important, because if you're above that dotted line inside that square, x is going to go from 0 to the parabolic sheet, and if you're below that dotted line inside the square, then x is going to go from 0 to the plane. So we need to find the equation of that dotted line. Okay, it's the YZ projection of that red curve. In other words, it's the YZ projection of the curve of intersection of the parabolic sheet and the plane. So let's find that. In fact, I'll stick with red so that you can see what I'm doing here. My plane is y equals 1 minus x, and my parabolic sheet is z equals 1 minus x squared. To get my YZ projection, what I want to do is eliminate x. X equals 1 minus y, x equals square root 1 minus z. Plus minus, sure, but I repeat, we're in the first octant here, only the positive applies. So 1 minus y equals square root 1 minus z, and yeah, that's basically it. So if I make y the subject, it would be 1 minus square root 1 minus z. If I make z the subject, I'll have what? Catch up with me, stylus? Thank you. Yeah, square. Am I right? No, I see. I put the square in the wrong place. Okay, let me fix that. I knew that was going wonky and I couldn't quite figure out why. There we go. So 2y minus y squared. Okay, I'm obviously a little bit error prone this morning. Let me just check that. 1 minus y, square root 1 minus z, 1 minus y equals square root 1 minus z, making y the subject, not that big a deal, making z the subject, I square both sides. Z is 1 minus that. That's 1, 2y, y squared. Okay, I think I'm right there. Okay, the reason, so I need to know the equation of that dotted line. That's important. And I'm going to ultimately require both y and z to be the subject of the equation because I'm wanting every possible order of variables. Okay, now I'm ready for my last two expressions of my triple integral, the ones where I begin with x. I equals integral, come on, integral, f, I'm just going to write f if you don't mind to save a bit of space, dx, let's do dy, dz, plus, and it's going to have to be a sum, dx, dy, dz. Okay, x is going first, x is going first, okay. So I'm going to remember that square with the dotted line? This integral is going to go with the top bit, and this integral is going to go with the bottom bit. So top bit, let's have a look. X is going to go from 0 to the parabolic sheet. What is it? It's square root of 1 minus z. Ugh. Okay. That is for that top bit of the square. So y is going from the dotted line. I'm going to have to write a bit skew here. I don't have enough space. Y is going from the dotted line. Y is that way. So it's no. It's going from 0 to the dotted line. Beg your pardon. Confusing myself here. Okay, y of course is measured horizontally in this picture. So y is going from 0 to the dotted line. I don't have enough space. 1 minus square root 1 minus z. Golly, that's a bit squashed. That's not so nice. Shall I rewrite that so that there's more space? I'm going to rewrite that so there's more space. I'm going to delete this, but not because it's wrong. I just want more space. It's just very squashy, and I can see it on my screen, but I suspect towards the back it's quite hard to see. You probably all have fantastic vision, unlike me. Don't worry, there's nothing wrong with any of this. I'm just going to write it out much more spacious. Okay, let's have a look. I'm wanting integral sign, leave a nice gap, integral sign, leave a lovely gap, integral sign f, dx, dy, dz, plus integral sign, lovely gap, lovely gap, lovely gap, f, dx, dy, dz, and this is there. Okay, all right. What did I say? I said x went from 0 to 1, square root of 1 minus z. Y is going from 0 to 1 minus square root 1 minus z. A little bit of extra space there, except that my stylus is going wonky. Okay, and that's for values of z that go from 0 to 1. Whew, okay. Bottom part of that funny little square. Y is doing that now. So x is going from 0 to the plane, 1 minus y. Y is going from the dotted line to y equals 1 for values of z that go from 0 to 1.
Sorry.
Yes.
I didn't get how you got the equation of the dotted line.
Okay, it's the YZ projection of the curve of intersection of the plane and the parabolic sheet. So that's quite a complicated sounding sentence. But basically, we have that parabolic sheet, and we have that plane, and they meet in that red curve. And that red curve is very important because it's the thing that differentiates the two different behaviors of the height, if you will, of the shape, given that yz is the base. So I'm wanting that dotted line. And that dotted line is not the curve of intersection, it's the yz projection of the curve of intersection. And I get that by taking my two surface equations, the plane and the parabolic sheet, and eliminating x, combining them in such a way that x is eliminated. Well, x is the only option to eliminate, in fact. And then you end up with that equation over there, which I've written with y as the subject and I've written with z as the subject, because I know I'm going to need both ultimately. Question?
So if you're looking at it on the y-z plane, on the right of that curve intersection, all the x values lie in the projection onto the y-z.
I'm not sure I'm understanding your question. Here's another way of thinking about it. I don't know whether it will answer your question, but here's another way of thinking about it. Imagine that we've got a whole bunch of points on the parabolic sheet, actually sitting on the surface of the parabolic sheet, and imagine they're a particular color. Maybe they're red, okay? And imagine we have a whole lot of points that are sitting on that plane. Sitting on the plane, and they're a color, let's imagine they're blue. Okay, so we've got some red points on the parabolic sheet, blue points on the plane. And then we take those points and we project them onto the YZ plane. What we'll end up with is, okay, I'm going to rub this out eventually because it's not officially associated with the notes, but what we'll end up with is all the red points from the parabolic sheet sitting there, and all the blue points that came from the plane sitting there. So if you imagine your surface, your two surfaces, your parabolic sheet and your plane, being colors, red and blue, and then projecting them directly, perpendicularly onto that square in the YZ plane, you'll end up with the point sitting like that. And so we're kind of doing what I've just described as projecting from the surfaces onto the YZ plane. In the integral, we're basically doing it the other way around. We're going from the YZ plane to the surface. And so the red points have to go, from 0 to the parabolic sheet, and the blue points have to go from 0 to the plane. Actually, maybe I'll just leave that there. Let me stop fiddling. Okay, let's do the very similar but slightly different one where x still goes first, but instead of yz, I'm going zy. Still dx, but z is going first. So x, I'll still do that, the red part, if you will, first. X is going from 0 to square root 1 minus z. Z will be going from the dotted line, from the dotted line. See that red up there at the top of the screen? That's the equation of the dotted line if z is the subject. So z is going from the dotted line to z equals 1 for values of y that go from 0 to 1. And then the second triple integral, which is to do with that blue bottom half of that square, x is going from 0 to the plane, z is going from 0 to the dotted line for values of y that go from 0 to 1. There you go. Done. Yeah, absolutely. So the integral has now been written 6 different ways, but they'll all give the same result if you actually work them out. So yeah, if I were actually wanting to do a calculation with this integral, I wouldn't choose either of these last two ones. I would choose one of the 4 earlier ones because they were much simpler and they all give the same result. I wouldn't choose to, because even though I do enjoy integration, life is short, so I would go for the...
No, man, but I'm saying in a test scenario, you won't tell us which to
No, very unlikely. That is correct. Yeah, no, for the sake of the audio, in a test or an exam, we will not indicate to you which order we would like you to do it in. In fact, we don't really care what order you do it in, as long as you get it right. Question? Okay, let's have a look. Which one are you talking about? This one over there where it goes y, z, or this one over here where it goes z? Okay, you're saying y. So y is going from the dotted line to 1. Okay. It goes with that square that's at the top there. Y is going, because y is measured, it's easy to think of y as being the vertical axis, but of course y is not the vertical axis, y is the horizontal axis in this picture. So in that integral over there, y has its, we're going from left to right, and the left is the dotted line and the right is y equals 1. And the dotted line is 1 minus square root 1 minus 7. The reason why I messed up the first time I wrote it down and is because I was kind of stuck into thinking that y was the vertical axis. Of course, in this picture it's not. Yes?
Please explain the dz in this one, how you got those limits to z.
For this last integral. For z. Again, let's have a look. In this one over here, in that triple integral over there, I'm interested in because z is going first and z reads bottom to top, because this is my z axis and that's my y axis. So z reads bottom to top, and because in this first triple integral, I'm interested in the top part of that square. In the second triple integral, I'm interested in the bottom part of that square. And in the top part of that square, I'm wanting z to go from dotted line to the top, which is z equals 1. So that's my dotted line equation. And then there's z equals 1 over there. And then for the second triple integral, where I'm interested in the bottom part of that square, z is going to go from z equals 0 to the dotted line. From 0 to the dotted line. From 0 to the dotted line. It's tricky, isn't it? It really is tricky. Because that dotted line there is kind of really important, but at the same time, it's kind of invisible. In your original drawing, you don't really see it. You see that lovely, beautiful, pure square sitting there on your YZ plane. And you have to actually do some quite serious thinking to realize that dotted line is a thing that's present in your problem. Okay, all right, on that note, I'm going to start a new section, which is what I wanted to start first thing this morning. I wanted to do that yesterday. Probably good I didn't start it yesterday, then we didn't have to rush it. Okay, I'm going to open a whole new document, because it's really quite a new section on linear transformations. Let's go for dark blue. Here we go. Okay. So first, in fact, let me actually write this down. I don't normally write this. I just usually say it when I teach this section, but let me actually write it down. Could you please keep quiet? This is going to look, for the first day or two, like it's got nothing to do with the rest of this course, because it's not going to look anything like calculus. So I want to explain why we're doing it. we're doing linear transformations, especially the geometric effect. The geometric effect of linear transformations. Then what we're going to do is we're going to move on to nonlinear transformations, especially the geometric effect if we approximate our nonlinear transformation as a linear transformation. So in fact, let me just, if we approximate nonlinear transformation as linear using something called the derivative matrix. Okay? And then we're going to move on from that to rubber, there we go, gone. We're going to move on from that to the role of transformations in the little delta A and delta V in double integrals and triple integrals. And from that, we're going to move on to something called Jacobians and coordinate changes in integration. Okay, so we're starting on a little bit of a journey here, and it starts with linear transformations, and it looks like it's got nothing to do with calculus, but it's setting us up for Jacobians and change of coordinates, which is very important and, extremely important. It's probably, you know how you do a course and then it falls behind you and you carry on and you do other things and then you think, gosh, I can't actually even remember what we did in that course. If the one thing that you end up remembering from this course is how to work with Jacobians and how to change coordinate systems and integration, that to my mind is the thing, the most valuable long-term benefit from this course. I'm not speaking as an engineer. I do not have an engineering background myself. That's from my point of view as a mathematics person. Okay, a map or transformation. So here we go. This is linear transformations. Mathematicians sometimes call them maps. We're largely going to be calling them transformations. A map or transformation T, going from Rn to Rm, we mostly deal with R2 and R3, as you know, is said to be linear if, and here's the definition of linearity, now that might look confusing, lots of little letters and arrows and gosh, there's even Greek letters, but what it says is very simple. Let's tease this apart into two separate things. In fact, let me even write it as two separate things. We could write, so this is basically amalgamating two properties into one expression. The one property says T of alpha x is equals alpha T of x. And the other property says T of x plus y is equal to T of x plus T of y. Okay, so there's basically two different properties that I've amalgamated into a single expression. And what that says is, if you have a vector and you want to do something to that vector, you've got something that you want to do to it. You want to double it, or you want to only double the x and not double the y, or you want to create a new vector where you, you've squared the first component and you cubed the second component or something. If you have some action that you want to carry out on a vector, that action is said to be linear if you take your vector and you multiply it by a scalar and then you carry out the transformation, you'll get exactly the same result as if you carry out the transformation first and only multiply by the scalar afterwards. That's what that alpha story is about. On the left, we've multiplied by the scalar first and then carried out the transformation. On the right, it's the other way around, but they're equal. Okay, the other property says if you have two vectors, it doesn't matter if you add those vectors together first and then apply the transformation, or if you apply the transformation to each vector separately and only add them up afterwards. Linear transformations, it doesn't matter. You can do those things. You've got choice of what order you do things in. Nonlinear transformations, if you do those two things, the left and right side of the equal signs, you won't end up with the same thing. Okay, and that's linear. That's what we call a linear transformation or a linear map. Turns out linear transformations are wonderful and glorious, and the angels come out and sing, because with linear maps we can represent them using matrices. And matrices are awesome, because as soon as you can represent anything as a matrix, you have access to all of linear algebra. You can do matrix multiplication, you can do matrix addition, you can do matrix inversion, you can do all of those beautiful things that you can do with matrices. Nonlinear transformations, you can't. And it's like your hands are tied. Whereas linear transformations, you have so much more ability to manipulate these things. So linear transformations are fabulous. And what you can do is, under certain special circumstances, nonlinear transformations, you can approximate as linear transformations and then go, ha, now I can do matrix arithmetic. Okay, all right. So that's the definition of linearity. Question? These are calculations being applied to vectors, correct. Every m by n matrix A, so here's a matrix, lovely, it's the first time we've seen matrices this semester so far, I think. Come on, stylist, you're being slow this morning. Woo! Every n by n matrix A defines a linear map, T going from Rn to Rm, by... Okay, now be careful with your mathematical notation here. This thing that's written on the left, we would use the word of. We'd write T of x. But this, there's no brackets, we'd say A multiplied by. Different, okay? So if you have a matrix, any old matrix, come up with a matrix. Multiply it by a vector of the appropriate dimension, and you'll get a new vector. So you've taken a vector, and you've transformed it through matrix multiplication. So we could call that action a transformation. And so what we've done on the left is we've written that in function notation. We say we've got this transformation T, and the action of transformation T on vector x is to take vector x and multiply it by this matrix A. What was I doing? Dark blue. There we go. Conversely, given any linear map, usually not written in matrix form, we can find a matrix. We can find an m by n matrix such that T of x equals AX for all x element R n. Okay, I think I've shown you that symbol before. An upside down capital A means for all. Mathematicians hate waste. Why use like 1, 2, 3, 4, 5, 6 letters and a space when all you have to do is one upside down capital letter? Boom. It's marvelous. You see some of the set theory expressions. There's no words, there's only symbols. Half of them are upside down from what you'd expect, and brackets, and round brackets, and curly brackets, and you can have like this huge statement written in like a tiny form. And then the mathematician walks away feeling very smug. Okay. Okay, I'm going to say something here that's not going to be particularly important until we get to exercises 78 and 79. Okay, so you might want to make a little note in the margin. Question, yeah?
Is it specifically the letter A that means for?
Upside down, yes. An upside down capital A means for all. A backwards capital E means there exists. There you go. That means there exists. And there are probably others as well. Why not? Why not? The columns, so this is an interesting little thing. The columns of this matrix, so you're given a linear map in some form that isn't a matrix form. And you want to find a matrix such that matrix multiplication represents the actions of the transformation. How do you find that matrix? Often it's very easy, sometimes it's tricky. The columns of this matrix are the vectors T1. Now it depends on the dimensions. Basically the columns of the identity matrix. Now, if it's just a 2 by 2 identity matrix, there will only be 2 columns. If it's 3 by 3, there'll be 3, etc. But I'm just generically trying to show the columns of the identity matrix. I'm actually going to leave what I've written here. And this is going to become important in exercises, what did I say? 78, 79. Yeah. So when we get to those exercises, I'll say, remember that thing I said about the columns of the matrix? And it'll be this. Okay, we are mostly interested in m equals n equals 2 and m equals n equals 3. Question, yes? Let's get to those exercises 78 and 79, then I think it'll become more clear. So I just want to put that there so it's part of the introduction, but we'll return to it later. Okay, I want to get 2 examples done, and we have less than 10 minutes. Exercise 54. Show that t of x is linear. Okay, so here is how linear transformation is frequently written. Now what does that mean? That means that if we're given a matrix that has an x coordinate and a y coordinate, we're going to create a new vector. That new vector's x component is going to be double the old x component. The new vector's y component is going to be the sum of the old vectors x and y. That's what that means. Let's prove that that is linear. The way that you prove that a transformation is linear is using the definition of linearity. Okay, so you're going to have lots, there's going to be a sea of little letters now. T of alpha x plus beta y. I'm starting with that on my left hand side. By the time I'm finished, I'm going to have, I'm going to scroll up, I'll come back down again. Where was my definition of linearity? There. This definition of linearity, I've started with that statement. By the time I'm finished, I'm going to have that statement. Off I go. Come back down to my problem. Hello. There we go. Equals. Okay. Let x equal x1, x2. Let y equal y1, y2. Okay, all right. I'm going to take x, I'm going to multiply it with alpha. I'm going to take y, I'm going to multiply it with beta. I have t of vector plus vector. I'm going to add those vectors. Now I have it in the form of t of a vector. Up until now I didn't, but now I do. I have t of a well-defined vector. I can now actually carry out my transformation. My transformation is that thing that I wrote first, straight after where I wrote exercise 54. So I now have a new vector which has as its x component 2 times the old x component and has as its y component the sum of the old x and y. Okay, now in a sense I've finished because I've carried out the transformation. But what I'm going to do now is I'm going to start splitting it apart. That is a big chunky vector. I'm going to split it up into the sum of 2 vectors where I'm very strategically going to place into one vector all the alphabets and into the other vector all the beta bits. And then I'm going to pull out the alpha and the beta respectively as common factors, or whatever you'd like to call it, scalar multiple of a vector. Ach, not beta. And ta-da! Those things in brackets there are exactly what I would have got if I'd carried out t on x and y right at the beginning. I've proven that t is linear. Question?
How did you go from the second line to the third line?
I applied t. Which I'm only able to do at that point because it's only at that point that I have t of a vector. Before that I had t of a sum of vectors. That's how you prove that something is a vector. Is linear, is a linear transformation. Proving that something is not a linear transformation is much, much easier. Because all you have to do is find a counterexample. So I'm going to do 55, but 55 is very quick. Oh, I've changed to black. Don't want to change to black. I want to change to dark blue. Beg your pardon. Sure, mustn't mix up my colors here. It says show that it's non-linear. Now this is a slightly a misleading one because it looks linear. If it had a sine x in it, or an e to the y, or a 1 over x, or even an x cubed, you'd say, that looks a bit fishy, doesn't look linear, doesn't look like what I think of when I think of the word linear, but that does, because those look like little straight line equations, so surely it's linear, but that plus 2 mucks things up. Linear transformations can't have plus a scalar, and we can prove that that's non-linear just by finding a counterexample. I'm going to do t of 1, 1. T of 1, 1 is 3, 3. I'm going to do t of 2, 2. T of 2, 2 is 4, 6. If t really were linear, then t of 2, 2 should be twice t of 1, 1. T of 2, 2 is not equal to t of 1, 1. And it would have to be, because that's what linearity says. Linearity says if you double your vector, it shouldn't matter whether you double before the transformation or afterwards. However, it does, because if we did the t11 first and then doubled it, we wouldn't have got what we do get if we double the vector first and then transform. So, not linear transformation. Okay, so here's the vector 1, 1. I doubled it to get 2, 2, and then I carried out the transformation and got 4, 6. If t had been linear, I should have been able to carry out the transformation on 1, 1, and then double it. Because linear transformations don't care what order you do that in. Whether you double first and then transform, or whether you transform and then double. That's the whole point of linearity. But that's not what you get, so it's not a linear transformation. So proving something non-linear is very easy. Counterexample. Proving that it is linear is a bit of a pain. You've got to do all that blah, blah, blah with the alpha and the beta. Question?
One of the tricks we learned last year is that if the origin doesn't map back to
Yeah, but I hadn't mentioned that yet. Linear transformations map the origin to the origin. However, some non-linear transformations do as well. But in this case, so there you go. Linear transformations always keep the origin at the origin. Some nonlinear transformations do as well. If we had applied t to the origin, we would have got the point 2, 0. We would have been able to say it's not linear because it didn't map the origin to the origin. If, however, it had mapped the origin to the origin, it wouldn't have been good enough. Because some nonlinear transformations do as well. Think of x squared, y squared. Nonlinear, but it transforms the origin to the origin. Okay, all right. We've run out of time in the period, so I'm going to stop. The trick with my system is that I need to save the video before I unplug the microphone. I learned that in the first week when we had a few crashes and I didn't know why. And then yesterday there were lots of questions, and then the next lecturer was in the venue and I just hurried through my procedure. And I unplugged the microphone before saving the video, and that meant the software crashed, and so we've got no video for yesterday. So I'm going to recreate yesterday's video when I have time to do so. So the notes are fine, but there's no video. So let me save the video before unplugging the microphone.